It is, it demonstrates at least as much my fault as it is anything else. So we're going to treat this as a learning experience. I'd like to go through and do some of these problems. Now, I think depending on when you took it, you got a version 1 or a version 2. So you just have to kind of bear with me. But I think we're going to be done with content here for the semester. We're just going to kind of spend the next 2 class periods talking about this test and trying to sharpen up some of these skills that you're for sure going to see again on the final. We talked about the final format, and I feel like you guys asked me all the questions you could possibly come up with about the final format. I'm still in kind of the proofreading stages, but nothing that I said is going to come or is going to be changed dramatically from what we had said before. What I would like to start with is the free response stuff. So I'm going to look at part 1 on the free responses.
Is it calculator or no calculator?
Sorry, part 1. That's the no calc. Okay. So you guys can share your scores here in a minute with each other and commiserate on how equally bad we all did. And that's fine. That's fair. I mean, I get it. I do be doing the same thing in your shoes. And just trying to laugh about it. I certainly wouldn't have if I were seeing it for the first time. Would I get 100 now? Maybe, but still, you've seen my propensity for making mistakes. The advantage I'd have is I can work much faster than you can because I feel much more familiar with all this stuff, so I'd have a chance to check things. But so this problem I thought should have been, my hope was that this was going to be pretty easy. It did not turn out to be that way, so let's talk about it and kind of what we were supposed to notice along the way. To show something like this is continuous over its domain, we need to do 2 things, right? So we can say that oops. So we know it's continuous from -1 to 2, where 2 is not included, 2 to 3, neither included, and then 3 to 5. 3 is not included because, why can I say that immediately? Braden? Right, so that's why we had to leave out the 2 and 3, but why can I say the rest of the stuff it's continuous everywhere except for that? Great. So we're a polynomial on each one of those 3 intervals. The question is, what about x equals 2? And what about x equals 3, right? That's the place where we could have some discontinuity because I need to make sure that the left side lines up with the right side. Our definition for continuity at a point is we need to show the limit as x approaches 2 of f of x equals f of 2. That's what we need to show. In order to show the limit at 2, well, I need to show the left-hand limit equals the right-hand limit. Everybody's okay with that? To do either of these limits, since f is a polynomial, I can just do direct substitution. So if I plug 2 in here, I have that, which is 0, which is the same thing as if I plug 2 into there. Now, I saw a lot of you guys really battling the arithmetic here on this piece. What could you have done to make the arithmetic much easier? Yeah, right? That's just going to be 9 times x squared minus 5x plus 6, which would be 9 times x minus 3 times x minus 2. And there the arithmetic should be definitely within your capabilities of plugging a 2 into that, saying that you're going to get a 0. Just pointing things out along the way. And then f of 2 is going to be the same thing as that. So we're good there, right? We have continuity at 2. Everybody's good? To do 3, we need to do the same thing. So we'll look at the left-hand limit and the right-hand limit. So when I do the left-hand limit, that's just me plugging 3 into this. But again, I'm not really plugging into there. I'm plugging in up here, and I can immediately see it's got to be 0, right? And then I'll plug in the right hand. So we're good there, especially since this is f of 3 also, right? Is everybody okay with how we did that? Okay. Again, this would have been like a chapter 1 question. Now, I asked you to do this for a reason, and it's for making sure on part C that we catch all the critical values. Yes, Beck.
Sorry, why did you use x equals 2 and x equals 3?
So anytime you have a boundary between your piecewise, we have to make sure that like the one end starts where the other end ends so that we have continuity. So those are the only places where you could have a discontinuity since every piece is polynomial. The only way you could get a discontinuity is if things don't line up. And that's what we were checking there, is to make sure everything lined up. Now, I told you it did, but I asked you to show it. A lot of us said they're polynomial, so you had it. A lot of us did check 2 and 3, but I don't think anybody did both. They did everything in between 2 and 3, and then 2 and 3. Maybe one person did, I don't remember, but almost nobody did that. Lots of us had one or the other, but few of us had both. All right. Part B asked for the derivative. So if our function f is piecewise, our derivative should be piecewise. Everybody agree?
Yeah.
How do I do the derivative of a piecewise function? I just do the derivative of each piece. That's it. Well, almost it. So I have negative 2x, then I have 18x minus 45, and then I have 2. But I have to worry about the domain now. Okay? So I know that I can't have a one-sided limit and take the derivative there, right? So the 2 and the 5, that was the negative 1 and the 5, that was the start and the end of my interval. I know automatically are going to be open when I take the derivative. Because I can't have a one-sided function and be able to take the derivative at that endpoint because I need a left-hand limit and a right-hand limit agreeing. Everybody's okay with that? So I know automatically those are going to end up being open.
Wait, they're what?
Open,
Oh.
as opposed to closed, which they are right now in F. And then I also need to worry about the changes in between, right? The transitions from one piece to the other piece. So I have to worry also about 2 and 3. So let's write down what we know. And then we need to check there to see if those limits, if the derivative exists there or not. Everybody's okay?
Why did you drop the equal to that?
So if I have something that looks like this, and I try to take the derivative there, there is no left-hand limit. So it can't have a derivative at that endpoint.
Okay.
Just by the definition of a derivative, right? Is that okay?
Yes.
Okay. So let's check at 2 and 3. So at x equals 2, I just need to look at the limit from the left and see if that's equal to the limit from the right. But now instead of using f, we're using f prime. So that is going to just be -4. That one is going to be 18 times 2 minus 45. The key here is that they're not equal. So the limit doesn't exist there. So the derivative is undefined at 2. Okay, so it should be strict less thans on both of the 2's. None of them are closed. Now I'm going to check 3. And we check it the same way. So when I do that, I have 18 times 3 minus 45, and then 2. Well, I don't care what 18 minus 45 is, or 18 times 3 minus 45 is, other than it's not 2. Right? What's that? It's 54 minus 18 or 45. It's not 2. So again, the 3 should be open on both ends. Isabel.
Was this just proving that they're open?
Correct. This is how I'm checking to whether those should be opened or closed, right? Because again, if I take the derivative of a piecewise function, I have to worry about those ends. Because if the slopes are coming in differently, then you have like a sharp corner where the derivative should not exist there, right? That's essentially what we just checked for.
Oh, so that's like determining.
That's just me checking to see if I have a sharp corner.
Oh,
Because the
okay.
slope from one end doesn't agree with the slope for the other end. Derivative can't exist at a sharp corner. That's what we did by doing that left-hand, right-hand limit at 2 and 3.
So then you find the derivative of the second part of it, and it doesn't exist. So you can't.
No, we everything other than, it's going to be a function, it just has an open circle
Oh, okay.
at 2 and 3, right? That's all it's saying. Not that the rest of the derivative fails to exist, just that, because after 2 and up until 3, we have a smooth polynomial. The derivative all through the smooth polynomial is going to be fine, just at the end point that we ran into a problem because we had a corner where one polynomial ended and the other polynomial started. Maybe I should have had you graph the piecewise first. That might have made a difference in catching that. If I asked you to graph it first, maybe you would have noticed the corners then, or maybe not. Part C then, we asked for the critical numbers. So right away, you should write down 2 and 3, because those are places where the derivative failed to exist, but are part of the domain. So far, so good? Why don't I have to worry about -1 and 5? Why didn't I worry about them? Because they're the ends. Yeah, because they're the ends. So like, again, if I'm looking for a local min and max, the endpoints aren't going to be a local min and max. By our definition, they could be an absolute min and max, but I'd be checking those regardless of whether they're a critical number or not, if it's an absolute. The other place we need to check then is where the derivative is equal to 0. So there's 3 ways I have to check that. I have to check negative 2x equal to 0. And I need to check that on the interval from negative 1 to 2. And then I have 18x minus 45 equal to 0. And I need to check that from 2 to 3. And then I have 2 equal to 0. And that I need to check from 3 to 5. Well, almost everybody saw that one. Most all of us saw this one, and even a lot of us reduced that to be like 5 over 2 or 2.5. And again, 0's in there, so it's okay. 2.5 is in there, it's okay. And then this one has no solution. So we should have 4 critical numbers. Because we had the 2 and the 3 from before. And now the 0 and 2.5. Beck?
Sorry, why were the discounters found before critical numbers?
Because that's places where the derivative doesn't exist, but the f does exist. So those are values that are in the domain of f, but aren't in the domain of f prime.
Okay, thank you.
Mm-hmm. All right. And then in part D, we asked you to find all the minimum and maximum values. So that's us doing that's including absolute mins and maxes as well as the local mins and maxes. So I'm going to do the absolute test because all that entails is just me plugging in my critical values and the endpoints. And if it actually, I think it asks for the values as well, so I would need to do this at some point for whatever I determined was my minimas or maximas or whatever here. Everybody okay with this plan? So when I plug negative 2 in, I plug it into the first part. When I plug 0 in, I plug it into the first part. When I plug 2 in, I plug it into the second part. When I plug 2.5 in, I plug it into the second part. What's that going to be? Nine over 4. So again, what's the easy way to do that? That's a half times a half times 9. So half times a half is a fourth. 9 times a fourth is 9/4. Sorry, my penmanship is sometimes not very good. And then if I do 3, that's 0. And if I do 5, that's 4. So if I look, my absolute minimum is at f of 2, which is 0, and f of 3, which is 0. So I have 2 absolute minima. And my absolute maxima, I have f of 0, which is 4, and f of 5, which is also 4. So I have 2 absolute maxima. But the point is that my minimum value is, absolute minimum value is 0, and my absolute maximum value is 4. Is everybody so far so good? Rita? So if I'm doing the absolute maximum or minimum test, I need to also test the endpoints of my domain. So you can only do an absolute minimum and absolute maximum on a closed interval. F was defined from -2 to +5 on a closed interval. Oh, I'm sorry. Was it supposed to be -1? Thank you.
I think it was -1.
Yeah, sorry, I just
Okay, that's
I just
that's
copied it
okay.
wrong. Yeah, I just. Okay, well that changes things a little bit because we lose a minimum then, right?
But then on the question, it says -2.
Well, that's just me being dumb then. How nobody asked about it, I don't know.
Yeah.
So that goes away. Right. Oh, sorry, not that one. Yeah, so that was supposed to be a -2, right? Oh no.
I don't think you have.
I think we just didn't write it down.
Oh, okay. Well, good.
It's fine.
There we go. It's all fine. There. Perfect. All right. Now, we should also determine locals. Now, I know these are locals. How do I know that? Absolute minimum maximums that are not at the endpoints are also locals. That's correct. So the only one I have to check then is the 2.5 to figure out if that's a minimum or a maximum. Correct?
It's not the 5.
Because that's an endpoint. Correct. So everything else we have there is good. So if I'll just do a first derivative test to do that, seems reasonable. You could do, actually, let's do a second derivative test because it's so stinking simple, right? What's the second derivative here? 18. Is that positive?
Yeah.
So that it was a absolute, or sorry, it was a local minimum at 2.5. Why did I choose that piece? That's where 2.5 lives. Right? So everything in 2.5, or everything on 2 to 3 is the same. So that's a local min at 2.5. I just wrote also local next to those. That's what we had circled them before I said it. I didn't write it down though, so I felt like I should do that. Isabel?
So we knew that f of 2.5 was a local minimum because the DC was positive.
Correct. Because the second derivative is positive.
So then doesn't that mean that we would have to plug in the negative so we determine if it's
I'm not doing an interval. I'm doing the second and not doing the first derivative test. You could do the first derivative test and pick like 2.25 and 2.75, but that didn't seem appealing to me because I didn't want to monkey around with no calculator and all those decimals. I did the second derivative test because it required literally no arithmetic, right? It just felt like it was going to be less time consuming to me when I looked at the problem. Is that?
Yeah, I just didn't know you could use a second derivative test to find like.
That's specifically what it does.
I thought that was only for like concavity.
So if you look at the second derivative, that tells you about concavity and about inflection points. The second derivative test tells you that if you have a critical value, or I should say a place where the derivative is 0, and the second derivative at that same value is positive, it's a minimum, local minimum. If it's negative, it's a local maximum. Uh-huh. All right. I'm going to skip that one, I think, for a moment. Oh, yeah, we need to talk about these L'Hopital problems. So let's go to the next part. I don't know that anybody did the second L'Hopital problem correct. which made me a little bit sad because
That was
I got a
so bad.
Beck did.
I got a funny. I got a
Nerd. I just made it sound like say Beck is a nerd.
Okay. Well, this is, and well, also the problem was that like most of us misapplied L'Hopital's rule on this one. So that's why I really want to talk about it. So the first thing we should do is do a direct substitution. So x becomes infinity, and 1 over infinity is like 0, right? And tan of 0 is 0. That's one of our indeterminate forms. However, we cannot apply L'Hopital's rule to this indeterminate form. We can only use L'Hopital if it's 0 over 0 or infinity over infinity. So I have to rewrite this problem as a fraction. I saw a lot of people check to see if it was indeterminate, which was great. Very few of us that went ahead and applied L'Hopital at that point wrote it as a fraction. So how can I rewrite x times tan of 1 over x as a fraction? There you go. That's, Jacob has it. We can write as tan 1 over x x to the negative 1. Because if I do the reciprocal of a reciprocal, that's like doing nothing at all, right? If I take the x, I make the exponent negative and put it in the denominator, it's like reciprocal to reciprocal, and it just didn't do nothing. Is everybody okay? We should check now just to make sure that we are in the form of L'Hopital. So if I do a direct substitution, the top is 0, right? When I plug infinity into 1 over x, the bottom is 0. And we're good to proceed with L'Hopital. Okay. And I'm going to think about, rather than tangent of 1 over x, I'm going to think about as x to the negative 1. I think it's just going to make life easier here in a minute. Okay, so we'll do our L'Hopital. When we do L'Hopital, we do the derivative of the top and then the derivative of the bottom. It's not a quotient rule. Saw some people doing a quotient rule here. What's the derivative of inverse tangent? That's not correct. That's tangent. It's
1 over 1 plus x. Oh, is that your
yeah. And then we also have, because it's a chain rule, it's going to be also then times the derivative of x to the negative 1, which is that. Oh, does it not? Why did I write? I don't know why I did do that. I'm sorry to whoever I said was Pierce. Did I tell you wrong? You're fine. I don't know. Oh, you know why it was? I did inverse tangent because it's supposed to be inverse tangent on the paper. I just didn't write it down in the right way. So well, he was not wrong. I think I probably said inverse tangent, but I definitely didn't write inverse tangent. So we'll call that like everybody made a mistake. It's not on your paper either?
No.
Oh, that's because I'm looking at the first problem. So all right, let's just back the truck up here. You know what? Sometimes we all have a bad day.
I had a bad day when I was thinking this one.
Yeah, I'm sorry about that.
It's okay.
Okay, there we go. Everybody okay here? Now, I saw some of us get to this spot, but then we did a direct substitution here. What should we do here first? Reduce. And look at that. Now you're in a spot where we can do a direct substitution and just be done. What's secant of 0? Nope. 1. Secant will be the same as cosine, so secant squared is 1 squared, so we're just 1. There's our answer. Braden.
Can you do this one with x cubed times e to the negative x squared?
Yeah.
I just
So we had, you said it was x times,
x cubed times e to the negative x.
okay. So I would do that. And we L'Hopital that. Let me just feel like I wrote something down wrong. Hold on a second. I'm pulling up the other one to look at this real quick. And this is the one that I cross this off and write a new ant problem here? Okay, this is the new one? Okay. You know what? I don't like the way this is looking. I'm going to switch. Yeah, and it was that way then, right? There we go. That'll make life much easier. And then I would reduce. Still can't do anything, so we got L'Hopital again. Right, because I still have infinity over infinity. But now I don't. So it'll just be 3 over infinity. That's 0. Three over infinity? Oh, this is is approaches 0?
Yeah.
Oh, well, you didn't tell me that. No, it can't be 0. Well, because it would just be like it'd be 0 over 1 in the very first step. You wouldn't even have to do anything.
Oh, okay.
Oh. Wow.
I wish I did.
Yeah. Well,
I don't-
Yeah,
This one would have equaled 0.
so hypothetically, what if I got 0? This was,
You had a different
did you take
problem.
version 2?
Hypothetically, it doesn't matter because we didn't count it anyways.
Yeah, we're not counting the test. I mean, it's all.
Yeah, it'll be fine.
But I probably did it first.
Okay. The other one that I definitely want to talk about was 14, which is the one with the picture. This one was almost, or was very similar to one that we had in the free response questions, right?
I was trying to base it off of that.
All right. So we want an equation that for the line tangent to G at x equals to 0. So I need to calculate G of 0 and G prime of 0, right? because the g of 0 is going to give me my y coordinate, and g prime of 0 is going to give me the slope. So there's my y coordinate. G prime would be e to the negative f of x times negative f prime of x. So when I plug that in, f prime of 0 is negative 1. So I'd have y minus e to the negative x equals negative e to the negative 3x. I'm sorry, 3 times x minus 0. And you can simplify that some more if you want to, but that's good enough. So far, so good? Yeah. For the next one, it says we're given an open interval and asked for the values where g has a local minimum. So we're going to be worrying about where g is equal to 0, or g prime is equal to 0, excuse me. And we said g prime was e to the negative f of x times negative f prime of x. So I can use the zero product property here. I know this part gives me no solution because I know an exponential is never equal to 0 because all we're doing is multiplying by non-zero numbers together. You can never get to 0. And then negative f prime of x equal to 0, same as f prime of x equal to 0. So I'm just going to go to my graph and look for my x-intercepts. I see negative 2, positive 2, and positive 7. Now to decide if they are minima or maxima, I'm just going to do like a sign diagram. And I'm going to look at what's going on before negative 2. Positive. So but I care about what is g prime doing. So that's going to be a negative times a positive, so that's negative, times a positive, so that's going to be negative, right? Everybody's okay? From negative 2 to 2, we see that f prime is negative. So g prime there should be positive. So that's a local min. Here we have, again, f prime is negative. So g prime should be positive. So this is nothing because you're going from positive to positive. We're looking at G, not F.
Yeah.
Going from negative, decreasing, to increasing. That's a local minimum.
Oh.
And here it would be a local maximum. So we conclude that x equals -2 is our local min.
I think that 7 local minimum.
Maybe I made a mistake. It happens. I had 2 different versions that I was grading, and sometimes maybe I got confused between the 2 of them or whatever. I think the only difference from one to the other is one was like negative f of x and the other was 2f of x in the problem. So like if you had that depend, yeah, I might have just got thinking I was looking at one problem that, well, I make mistakes. You guys have seen it. I apologize. The next part asked is G prime of 2 positive, negative, or 0. Well, I'm going to start with G prime of x, which we said was negative e to the negative f of x times f prime of x, right? To differentiate that, I need to use the product rule. So I'll take the derivative of the e to the negative fx times f prime of x, and then I'll have negative e to the negative f of x times the derivative of f prime of x. And what I'm going to do there is I'm going to notice, okay, those guys cancel each other out. If I factor out an e to the negative fx, I have f prime of x squared minus f double prime of x. So if I want g double prime of 2, so I know this piece, that's always positive, right? Because it's an exponential. If I look at f prime of 2 at my graph, that's equal to 0. And if I want f double prime of 2, I notice that f prime of 2 is a maximum. So the derivative at a maximum is going to be also 0. So if we want to find the mins and maxes for a function, we do the first derivative and we look for where the first derivative is 0. Same idea, right? So it's just if the graph is a min or max there, the derivative of that graph is going to be 0 at the mins and maxes. So what can I say this should equal? 0 minus 0 is 0. 0 times positive is 0. That was one of my favorite questions because you really had to like understand what you're looking at. That was I think one of the harder questions on the test, in my opinion, because you really had to be able to use that graph and think about the second derivative as the first derivative of the first derivative and use all kinds of like really some deep understanding there. So if we want the average rate of change for G prime, that should be this, right? So again, I have to use my formula that I made earlier for the derivative. And you might be thinking to yourself, Mr. Kulik, how am I supposed to do f of 7 or f of 2? I wasn't given any of that information. Doesn't matter because the first derivative at 2 and 7 is of f is 0. Just pulled that from the graph. So it should be 0. A lot of us are using f here instead of g. And some of us use g instead of g prime. The vocab here on this one felt like it got away from us a little bit on that one, but that was the idea. And then like 15 there seemed like it was just, we ran out of time and got pretty raggedy. Let's do 15 since it seems like a lot of us didn't have a chance to really do that and do a good job with it. Does that sound okay to everybody? This one felt like the one everybody just kind of like I quit because it was the last one on here. That's great. Again, I thought my intention was for this to be rather easy, particularly since you had a calculator, that the trig stuff landed in the calculator section as opposed to the no calculator section. I thought I was going to be doing you a favor. Okay. So if I'm looking for increasing and decreasing, I need first derivative. So what's the derivative of sine squared x? That's a chain rule. So 2 sine x cosine x. Am I just looking at the wrong version?
Yeah, you are.
Okay, whatever. It's the, right?
Cosine squared x. Yeah, that's how the rest goes. No.
It's like the same problem, right? Like if you can do one, you can do the other kind of thing. So like they're pretty darn equivalent. If you want, I can update it, but I figure fair is fair. The other people that have the other version have been watching the wrong problem the whole time. Let's do one of theirs, I guess. Okay. So there's my first derivative. Now what do I do? Set it equal to 0. Yeah. Because to do this, I really just am going to kind of be doing the same thing I would for a first derivative test, right? How do I solve 2 sine x cosine x plus 2 sine x equal to 0? Great. He said factor out 2 sine. And once you've got that factored, we can set each piece equal to 0. So sine is equal to 0 at 0, but we're going all the way to 2 pi. Where else? You could check it on your calculator, but again, unit circle, the AP expects us to memorize these things. So cosine x equals -1, where does that happen at? Just that one. So this one, I think, the version 2 people had the easier problem because I think you only have like one critical value here. I think the version 1 people, I think you guys get 3 out of this one. So I'm going to pick a test value. I think the natural test values to pick here would be pi over 2 and 3 pi over 2. So when I plug that in, sine of pi over 2 is 1. Cosine of pi over 2 is 0. And then sine of pi over 2 is 1, so that's going to be positive 2. Sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0, so I'd have 0 plus 2 times -1, so that's negative. So we are increasing from 0 to pi and decreasing from pi to 2 pi. If I wanted the local minimum and maximum values, that was part B. Well, I know that this is a local maximum. At f of pi. And when I plug that in to f, sine of pi is 0, and cosine of pi is -1. And that was our only critical value, so there is no local minimum here. I think if you had version 1, there would have been both, because you had more critical values. Part C asks for the intervals of concavity and the inflection points. This one was quite challenging because the derivative got pretty nasty. So remember that our first derivative was 2 sine x cosine x plus 2 sine x. So to do the second derivative, I'm going to have 2 sine x, and then the derivative of sine x is negative cosine x, and then plus the derivative of sine x is cosine x, and then times cosine x, and then plus 2. Oops, cosine x. So when I FOIL this out, I have -2 sine squared x plus cosine, or 2 cosine squared x plus 2 cosine x. So far, so good. Okay. How do I solve this now equal to 0? Well, you can get rid of the 2, right? That's fine. Talika said factor out the 2, but let's just divide it to both sides since it's equal to 0. We can just dump it. Sine squared plus cosine squared is, but we don't have that. We have negative sine squared plus cosine squared. What you should do is you should take sine squared and turn it into 1 minus cosine squared to get everything in terms of cosines. And then we distribute the 1 through. The cosine squares do not cancel. So when we combine like terms, we have 2 cosine squared plus cosine x minus 1. That does look a lot like a quadratic. Can we try to factor that like a quadratic? Let's try it. So we know it's going to be 2 cosine x and a cosine x. And then we're going to have 1s over here. We just have to get the plus and minus in the right place. Where should the plus go? Where should the minus go? Minus plus is correct. Because we need the 2 cosine x to be positive. Okay? So now we can apply the zero product property and set these both equal to 0. So where is cosine equal to 1/2? Unit circle. It's pi over 3. And you're just saying it to say things, but that's okay. Where's the other one at? Should be in the 4th quadrant, right?
Yeah.
All silly turtles crawl.
11 pi over 6.
So you 5 pi over 3.
Oh, my guess is right.
Yeah. I was in the right one.
My guess is right. I was
And then where's cosine equal to -1? So there's my possible inflection points. So we got to pick some test values now. Yuck.
0, 1.
You would 0 is probably okay. I would not choose 1 because 1 is not bigger than pi over 3. I might pick pi over 2 though. 1/2 is bigger than 1/3. And I might pick 3 pi over 2. I might do 2 pi. Does that sound okay?
Wait, I have a question.
Sure.
So, like, 0 and 2 pi are the same. Once you combine those zeros, can you just fill that sign out for 2 pi also? Or?
Sure. So if I plug 0 in, cosine of 0 is 1, 2 times 1 is 1, minus 1 is 1, and then a 1, so that's a 2. Well, I don't care. I just care it's positive. If I plug pi over 2 in, that's 0, so that's -1 times 1, that's negative. Pi over 2 in, cosine is 0, so that's -1 plus 1, so that's negative. And then if I plug 2 pi in, that is 2 minus 1, so that's 1, and then plus 2, okay, so that's positive. So we see that those guys are inflection points. We are concave up from 0 to pi over 3, and then again from 5 pi over 3 to 2 pi, and we're concave down from pi over 3 to pi, and then from pi to 3 pi over 2. the algebra there got rough because you had to use some real triggy. You had to get real triggy with it. Yeah, that was a hard one. The solving got pretty tough there by the end of that. That's the problem with the second derivative. If it's not a polynomial, it tends to get more complicated as you differentiate if it's not polynomial. Yeah, so that's tough. And then part D was me trying to be nice and throw you a softball here at the very last question. So it says, find all C such that C is on the interval from 0 to 2 pi, and f prime of C is equal to this. What was f of 2 pi? Sine of 2 pi is 0, and cosine of 2 pi is 1, so that's -2. And what's f of 0 going to be? The same thing? So what are we really asking for? The solution to where the first derivative is 0. We did that already in part A.
Right.
That was me trying to be helpful at the end and give you like here's the last question, same as the first question. I don't know, I'm trying. When I write these, I try to find like here's a question, like if you know what you're doing and you got that, it's like we already have it. Yeah. Just most of us didn't even get this far, it seemed like. And that's fine. What I would ask for you guys here before next class, take a look through this. We did a lot of the stuff that I found was there's one more that I want to do. And this one it was the last multiple choice in the no calculator section, because some people wrote like an entire page for this and did like so many L'Hopital's.
Five.
I wrote a bunch. I got
So
Did you get
the direct substitution, you should have gotten infinity over infinity, right? Or negative infinity over negative infinity, but whatever. So we can L'Hopital this. Natural log of 0 is negative infinity. So we'll do a L'Hopital. It's just me doing the yeah, I mean it's 1 over, it's just me doing the derivative of a natural log, right? Oops. Okay, so I did my L'Hopital. So if I take a look at what I have, I'm just doing some simplification now. How do I divide two fractions? Multiply by the reciprocal?
Yeah, that's right. I actually did know that. I did know.
Okay. If I look, I can factor an x here and also here, right? Everybody see that? Can reduce that x, and now when I do a direct substitution, I have 0 plus c times 0 plus d over 0 plus c times 0 plus d. Should be 1. I saw so many of us just like L'Hopitaling and like did L'Hopital like 3, 4, 5 times, and I just felt really bad. Just like, oh, guys, it was right there for you. I do, Cheech. No, I trust you. You're welcome. The other route that you might have chosen to do was try to use like the change of base formula for a logarithm to make this one thing where you could reduce the fraction then. Nobody, it looked like, attempted to do that. I would have been surprised if you came up with that as an idea. But you remember, like, that's the change of base formula. So you could have tried to like do something with that. I would not have. I think that would have made life worse, but I wrote that so as that it wasn't supposed to be a eternity-long L'Hopital problem. But all right. So for next time, go back through the rest of the stuff on this test that we didn't talk about yet. Highlight a couple of things that you definitely want to talk about, that you've sat down and you looked at and you thought about. And we'll do that as well as take questions about optimization. Does that sound like a plan, Pierce? I don't know. We didn't do 4-6. Yeah, I probably forgot to update anything. Did I put anything in there?
No, that's why I was confused.
Yeah. I just, at this point, like, I don't even think I need to grade another homework assignment. Like, you guys can just like do as much as you need to make sure you got it. And then like, I'm not going to look at anything else. Like, I'm going to, if you have missing stuff, give me your missings by Friday or Thursday, I should say. And then if you had a makeup to do or whatever, if you're doing a retake, I mean, let's worry about those. Everybody else, just like your score is your score then probably, which feels probably fine heading into the final. Isabel?
You know how for like every test you would write down like studied these specific problems. Do you think you could do that for the test we just took? Because I think I should do like more practice for a final, like that aren't the test.
Well, to be honest with you, like, so like this free response question 1, I basically just took this, gave you a different graph, but it was basically the same problem. And then, let's see.
There's only one question on the Wait, it was out of three. What was it? Oh, 48.
So that one was real similar. And then,
Hey, that's good. That's actually good. I got like a 7. That's so funny. I didn't even realize. I didn't do so much.
yeah, Isabel, I mean, so the piecewise one I just kind of invented.
Yeah, that's why I was like, kind of just.
But I mean, anyways,
I tried my best.
the related rates one I thought was relatively similar to the free response related rate ones. Where did those go to? You know, I thought it was reasonably similar to this,
Yeah.
or that, you know, like, and then then there was just like that last one, which was just like every other, you know, like increasing, decreasing, max, min. Like it was like a lot of those ones that we've done. It just was like had a lot of trig in it, you know.
So just like practice, so just like know how to find like.
Yeah, so like there's only so much I can do with still making the problem like algebraically reasonable. But even worst case scenario, like had you found the second derivative, set it equal to 0, and then used your calculator to find the solutions to that, like that would have been okay. You know, like you could have done that and just found the zeros and wrote those down and like use that to do the, you know, to like figure out your intervals, and like that would have been okay. You know what I mean?
Study like our old tests.
Yeah. Yeah, I would think again, like there's that true false section that's really kind of the emphasis is on like theorems and vocabulary and definitions, and like you have to kind of understand the stuff.
Do you have a Quizlet on those? Or? Yeah.
Uh,
I can probably find one online, but like if you have one.
I don't have one made. Okay. Beck?
Is the double test line already?
Depends on when you filled out your form, because I did it at one point last week, but it was probably pretty early last week. So it's on my to-do list still this week to make sure that everybody's got something entered. Yes. What did you already?
I just did. I was waiting for
You just did. Okay. Yes. Thursday, you said?
Yeah.
What test version?
Number 2.
Okay.
Is that fine?
Yeah. Test 2 Thursday, study hall. Okay. Thanks, dude.
Right.